Hello, good afternoon. My name is Tara, and this is a Linux kernel power management overview presentation. This presentation itself is adapted from another presentation given by Kevin Hillman named An Introduction to Kernel Power Management. It has been presented at a few conferences and a few past Linaro Connects. So the session is not meant to be a deep dive into any of the PM frameworks in Linux kernel. It's more of an overview. So let's start with why do we need power management. The main idea is to reduce overall energy consumption, which in turn probably will reduce cooling requirements, lower heat dissipation, which in turn saves money, gains more system stability, lesser environmental impact, and when you come to probably embedded devices, IoT devices, portable devices, power management can give you better battery consumption. So the goal is to consume as little power as possible in a given system state for a given configuration or for a use case. And as the SoCs have evolved over time, the solution in the kernel has also evolved over time and has become quite complex. So broadly speaking, the power management solution in Linux framework can be classified into two: static power management and dynamic power management. Static power management deals with how to save power when system is inactive for long periods of time. Like if you're talking about a desktop system, the system is idle for let's say 30 minutes or an hour, what to do with it? Or on a phone, when you press the power button, what to do with it. Whereas dynamic PM, on the other hand, deals with power savings when the system is active. Like system, let's say there is video playback happening. So what do you do with camera, which is not connected to video playback? What do you do with the peripherals that are associated with video playback? Do you run them at full throttle, or do you kind of try to save power there? So that is the dynamic power management portion of it. As far as the frameworks in Linux kernel is concerned, the frameworks pertaining to static power management is quite evolved. It has been there for some time. There is some activity happening on it, but no major framework is getting developed as of now. For dynamic PM, on the contrary, it is quite evolving. Like I mentioned before, as the complexity in SoCs evolve, the dynamic PM frameworks are getting evolved. So moving on to static PM, the framework in Linux kernel that deals with static PM is known as suspend resume framework. So broadly speaking, the suspend resume is triggered from the user space. When you press, like I mentioned, when you press the power button on the phone, the suspend resume framework gets evoked. How? There is a sysfs file that is provided, and you can echo various states into it. The file is syspower state. So generically what it does is the suspend resume framework freezes the user space tasks. There is this concept of task freezing. It suspends timekeeping, puts all the I/O devices into low power states or deep idle states. And then depending on the value that is echoed into this sysfs file, some other power saving steps are taken. So I'll go through it. So the suspend to idle, which is probably the state with the minimal latency, and the only extra step that is taken here is to put all the CPUs in the system to deep idle states. There is power on suspend or standby, where in addition to putting CPUs into idle states, non-boot CPUs are taken offline. There is suspend to RAM, where the RAM is memory is put into self-refresh mode, all non-boot CPUs are taken offline and the boot CPU is powered down. And finally, there is suspend to disk. It is commonly known as hibernation. It is not very commonly seen on embedded devices, whereas it is more common prevailing on desktops and laptops. Here, a snapshot of the system is saved onto a persistent device and the entire system is powered down. On boot up, the system boots up normally, but at some point during boot up, the image is restored back from the persistent storage, and the system is restored back to the state where it powered down from. Okay, so I think this it's a big presentation and we've moved through frameworks, so I think it will be better if there are questions, we address it framework by framework instead of waiting till the end probably. So suspend resume, what should subsystems do? In the PM code, there is this main structure known as dev PM ops. You will see it quite throughout the presentation for various frameworks. Every device will have a dev PM ops where the device should hook up these structures, especially the prepare, suspend, resume. And these are the device hooks. The framework also provides platform-specific hooks, which is meant to be one per platform. So when a suspend is triggered, the platform hook gets called first, which in turn calls the device-specific hooks. And similarly for resume. Again, once the system suspends, how do you wake up? Typically, wake up is triggered by a user event. It's either you pressing the power button on the phone, or a keyboard event on a desktop, a mouse event on a laptop, something like that. So what should devices do in order to enable it? So there is device init wake up, it is a way of devices to let the PM core know that it is wake up capable, and if it's wake up capable, whether it is enabled or not. Then typically all these wake up events are triggered as interrupts, and so enable IRQ wake and disable IRQ wake is a way of notifying the interrupt subsystem as to whether a particular interrupt is wake up capable or not. Once the wake up occurs, the devices are supposed to notify the PM core via PM wake up event that, okay, an event has occurred, so do the necessary processing required. Wake-ups can also be enabled from user space. So every device has a node associated with it in the sysfs. It's under sys devices. And so under the sys devices entry, there is a subdirectory for power wake-up where you can basically enable or disable the wake-up sources associated with the device. Okay. Okay, I think that is pretty much it.
So if you set this device wake up, then that interrupt will not be masked when the system goes to suspend. So does it work this way, that when you mark the device as wake up capable, then the interrupts associated with that interrupt will not be masked during suspend, so they will be able to bring the system back online?
Yes, that is the idea, but then the drivers have to work with it. Like, especially if, like, for example, if you're doing it from the user space, there is a provision, but then the driver has to run with it, has to take it and do the necessary processing to keep the interrupts enabled.
Okay. Yeah, I get it. Thanks.
Yeah. Okay, so let's move on. So nothing much. So this is all there. That's quite stable in the Linux kernel. There are bug fixes happening once in a while, but nothing major is evolving here. Okay. So moving on to dynamic PM. Let us see. So like I said, it is use case based power management, the system is running something, so what do we do? When the system is running, how best can you save power? It's the basic concept behind dynamic PM framework. So there are a bunch of frameworks that cater to it. There is CPUFreck, DevFreck, OPP, GenPD, Runtime PM, Clock Framework, Regulator Framework, CPU Idle Framework, it's not mentioned here. So some of it are front-end frameworks, that is devices actually, or CPUs or devices actually interact with it. Some of them are back-end frameworks where it does most of the bookkeeping or the back-end activity. We'll go through most of this. So, okay, so let's move on to CPUFreck. So there is this concept of DVFS, which is dynamic voltage and frequency scaling. The idea is that there can be multiple frequencies at which a device can operate at, and there can be multiple voltages associated with some of these at least some of these frequencies. So I think we should probably go through this first. So this pair of frequency and the associated voltage, the tuple, different SOCs name it differently, but the common term in Linux kernel is operating performance point, or OPP. These values are usually defined in the device tree. It is defined per device basis for a CPU, for a GPU, for any other device that has various frequencies associated with it. And there is an OPP framework in Linux kernel. It kind of forms the backend for the DVFS itself. And the idea here is that devices need not function at the highest possible frequency, at the highest possible voltage always, even when they are active and they are catering to a use case. Depending on the performance requirements, frequency, and in turn voltage. The important part here is voltage scaling, because that is where the power saving comes from. So frequency and in turn voltage can be scaled depending on the performance requirements so that you get better power savings as a system. So CPUFreck is the framework that caters to DVFS for CPUs. The idea is to select the best possible OPP for CPUs based on certain constraints and requirements, and the entity that provides these constraints and requirements is known as governors in Linux kernel. So governors are pluggable. There are various multiple governors in the system today. Anybody is free to write a governor and upstream it, probably, but yeah. So I'll explain a little bit on the governors. So there is performance governor, power save governor. They are probably the simplest governors in the system, where the performance governor says that always choose an OPP that gives the best performance. Power save governor says that always choose the OPP that gives the lowest or the best power savings, let me put it that way. And then there is user space governor, where the OPP can be chosen from the user space rather than the kernel driving it. Yes?
I can speak up. So what is the state of schedule as far as performance, power savings is concerned? And is there any plans of getting rid of on-demand?
I don't know if there are any plans of getting rid of on-demand.
Are we on parity with schedule?
So we are not removing the on-demand governor for sure. But what was the other question?
So what's the state? Is schedule and on-demand, are they in parity in terms of performance and power for most of the use cases you've tested on? No. If schedule is as performant and as power saving as on-demand, why don't we get rid of it on-demand? You need both of them? I don't. I'm saying get rid of on-demand. Yeah.
Because on-demand is used for the old system mostly, and even it is the default governor for x86 right now as well. So the problem is, if shifting a governor produces a regression, who is going to test for the older platforms? So these things will just stay. They will not get removed for sure. But I think the default for ARM right now is schedutil. Even for x86 people, it is not the default from the config, but still people use schedutil nowadays.
And another thing is that the load tracking is not available for UP system, so if uniprocessor. So you can't use schedutil on non-SMP system.
So the follow-up question then is the AOSP tree now moved to schedutil from interactive?
Yeah.
Okay.
Okay.
I guess more kind of question for Videsh too, or you, Vasant. So why don't we do PEL support for UP and try to get schedule working on UP too?
Mainly because at the beginning the load tracking was only for SMP system because it was used for doing some load balancing, and you don't have any kind of between CPU load balancing on uniprocessor. So if you look at with only one processor, the only useful use case would be to enable schedutil for uniprocessor.
Is there something you can do?
Yeah, I think it's just that nobody
Okay.
push a patch because.
Okay. It's just a matter of deleting the ifdefs,
Yeah.
or just a more trick
Yeah.
to it than.
Yeah, and probably, yes, some part will be useless, so you need to partition correctly what you have to enable or not for uniprocessor.
Okay.
That's all.
Do we have any UP systems nowadays?
So like for say low-end IoTs or whatever, right? Like we currently use on-demand. If I could switch to schedule, like you just need to support one of them. Right,
Oh,
sounds
yeah.
good.
But again, going back to your point, I don't know if there are, at least I haven't seen concrete test results which says compares on-demand versus scheduled, at least, I don't, unless someone corrects me. Yeah. Yeah, that's probably good enough, yes. Yeah, yeah. Okay, so where were we? So I talked about user space where the OPPs can be controlled from the user space. Then there is on-demand where the idea is to track CPU load and to take decisions depending on the CPU load. The governor itself scales OPPs in steps depending on CPU load and scales it down as in steps as well. And there are a bunch of knobs associated with this governor that is quite tunable, like the frequency at which the CPU load is tracked, the speed at which the OPPs are scaled up and scaled down and stuff like that. And there is another governor called interactive, which is probably more used in, mostly used in Android. It can be considered as on-demand plus kind of governor. Where the idea is upon an interactive event from the user space, like let's say a touch screen activity or a keyboard activity, the OPP is boosted up to the highest possible OPP. It doesn't do the stepwise scaling, and then it lets the stepping down is the scaling down of OPPs is done in a stepwise manner in interactive. Oh, okay. Okay.
And we do the touch boost from user space.
Oh, you do touch boost from user. Okay. Okay. And finally, there is schedule, which is the latest governor in the kernel. The idea is that if on-demand, so why it was developed is if on-demand was tracking CPU load, isn't the best place to track it at the scheduler level. And that is what schedule does. It kind of collects a bunch of information from the scheduler regarding CPU load and other stuff and makes the decision on what should be the next OPP for the CPU. So every platform can have a driver for CPUFreck. The generic driver used in ARM today is CPUFreck-dt.c. Okay, so CPUFreck is all about CPU scaling. There is something called DevFreck, which does DVFS for devices. It is quite similar. There is governors like on-demand and performance, power save. And the idea is to select the best OPP for devices, again based on the constraints and requirements provided by the governors. I think we went through this. Okay. So that was the active power management, the active part of the active power management. And now there is an idle part to active power management, where the idle time is more like milliseconds and microseconds and not minutes and hours together. So, whatever is said here, so it is basically periodic idling in between tasks. So what do you do with devices at this point? What do you do with CPU at this point when the idle time is really, really small? The frameworks, there is CPU idle to idle CPUs, and for device idle, there are a couple of new frameworks. It's Runtime PM and generic power domain framework. It's been there for a few years now, but it is relatively new in the Linux kernel. Okay. So CPU idle, so there is this concept of depth or so there is this concept of CPU idle states or C states. The term itself comes from ACPI world, and there is this concept of depth. Basically, deeper your C state is, more is the power saving, but so is the latency. More is the latency to enter and exit out of the state. And the C states are defined in the device tree. It is defined per CPU basis. So on the left, what you see is an entry from the device tree. I don't remember which platform I pulled it out of, but so the main pointers here is the entry latency, exit latency, and minimum residency. So the idea is there is a cost associated with entering and exiting out of any C state. And if the CPU doesn't remain in that particular C state for minimum residency, there is no power saving per se because of the entry and exit latency. That is the basic idea here. There are governors associated with CPU idle. I think I will talk about it in the next slide. So there are governors associated with CPU idle that kind of helps in decision making on which is the next C state to choose. As far as drivers are concerned, you can have a driver per platform, but again, in most of the ARM devices are using CPU idle ARM.C. Okay, what else? Okay, so moving on. So the governor, there are two governors, menu and ladder. I don't know if anyone is using ladder. There is menu, which is always used. Chooses the C state to enter the next C state for a CPU to enter based on a few parameters. The first one is latency limitations that are imposed by QoS. There's a quality of service framework in Linux kernel, which we'll talk about at the end of the presentation. So basically, devices can put a limitation saying that I need the CPU latency to be at a level, and so the governor kind of takes the latency limitations into account and compares it with the entry time, exit time, minimum residency to choose a next C state. The next predictable event, which is the timers. So if the idea here is if the system already knows that there is going to be a timer activity at a certain time in the future, there is no point in entering a C state whose minimum residency is more than that, because you anyway have to come out of it, and you kind of lose the power saving benefit. And there are some magic multipliers which have been there for some time now. Oh yeah, sorry.
So for this entry, exit time and minimum residency, how do you, I mean, is there any mechanism you decide the values for those numbers, or do some load testing and then figure out what should be the value?
So there is no prescribed test or anything. I think it depends on platform to platform. It varies from SoC to SoC. Some of it is defined based on past experience and stuff like that. Some of it is just tweaked as you develop the system. But yeah, so there is no one set rule for defining the entry, exit, and.
So these values are very specific to even a same platform can have different performance based on, every single entity will have different values. So are they hard-coded in device tree? Can we later on, let's say, we learn that the best suited value for this board is, let's say, some ABC values. So do we change it later on, or can we change it?
There is no provision to change it from user space or anything, but I kind of don't understand your concern. Why do you say that it changes from, for a platform, why do you say it changes from device to device? It's kind of surprising. Okay, you can use this.
Yeah, it needs to wake up from idle. So, I think it's mostly on a chip-to-chip specific thing, and I don't think it's going to change. Like, for a CPU, if you need to flash the cache, if it has a bigger cache, it's going to take a longer time. So it's mostly a measurable thing. There might be some worst-case scenarios where the number might go higher, but typically it's fairly consistent and measurable. So the worst case could be like if you want to turn off the PIMIC power supply to the CPU. If the bus itself is contented, like a lot of stuff going on the bus, you might not be able to talk to the PIMIC. Your time to go to idle could increase or exit could increase. But generally it's on the same ballpark. So you can just hard code it in DD. And board to board, again, it's kind of unlikely to change unless you have to talk to a PIMIC outside the chip. Then it could change. But again, not likely to change a lot. At least from my experience at Qualcomm.
I didn't get it. What's that?
Do you specify the entry and exit time for each C state in device tree?
Oh, yes, we do. Yes. There are several entries.
This
yes.
mic woke up.
So yeah, back to your question, there is no user space entry to control any of these times. It comes from the device tree. Okay, so where were we? I think I was talking about the multipliers. So there's nothing. So the basic idea behind the multipliers is to aid the governor to force the governor to choose a shallow C state if the CPU load is high versus choose a deep C state if the CPU load is low. And then off late there is this IRQ prediction, which is quite recent, which is an attempt to predict along with instead of just predicting the next timer activity, also predict the next interrupt activity, IO interrupt activity. So that's quite a recent development. What else? Okay, I think that is it about CPU idle. Okay. So moving on to the device idle. So here the idea, it is per device idle. It is quite different from static PM suspend resume where the entire system is shut down and all devices are put into a low power state. This is more like per device idle. It is driven by the device. The idea is that device driver is probably the best place to track the idleness or busyness of a device. So device driver can trigger the request for idle and the request for being active. No dependencies are taken care of except the parent-child dependency in the device tree or the device driver model. And there is no user space idling. It is again per device basis. There is no freezing of tasks or any of that stuff that is associated with suspend resume and static PM. Okay, so what should a device do to subscribe to the Runtime PM framework? The device driver should register a few hooks, at least the runtime suspend and runtime resume hooks. And when the device driver knows that the device has to be active, it should let the PM core know that via PM runtime get or PM runtime get sync. And similarly, when the device driver knows that the device is going to be idle, let the PM code, the runtime PM framework, know that via runtime PM put sync, or runtime PM put auto suspend. And the rest of it kind of gets taken care of by the runtime PM framework internally. It kind of keeps track of the clocks associated with the devices in the device tree and takes care of shutting down the correct clocks based on use count and all that. I think we'll talk about use count, yes. So internally, runtime PM is based on use count. It maintains a counter per device. And if the use count is 0, which means it knows that the number of requests for it to be for the particular device to be active is 0, it calls into the runtime suspend hook that has been registered by the driver. And the driver is then responsible to prepare for suspend, do stuff like context save, enable any wake ups if needed, and etc. Similarly, if the use count is 1, the framework calls into the runtime resume hook and lets the driver know that, okay, the device is going to be active. Is there any context restore to be done? Is there something else that needs to be done at that point? So that is basically runtime PM. And then there is this generic power domain framework. There's this concept of power domains where devices can be grouped together depending upon devices that can be power gated together are grouped together. Let me put it that way, that are power gated together can be grouped together. So there's most of the SOCs do specify some kind of physical groupings nowadays, and the generic power domain framework has been evolved to have a kind of logical grouping provided by the software to taking into account the physical grouping by the SOC. It is based on runtime PM, as in the device drivers need not call directly into the framework. Typically there are a few special cases, but device drivers need only to do a runtime get or a runtime put, and the rest of it gets taken care of internally. The power domains are specified and defined as part of device tree. There is power domain definition in the device tree. There is also entries for each device to specify the power domain associated with it. Once that is done, there is nothing else that needs to be done by the drivers. The framework takes care of populating all the needed structures and associating each device with the correct power domains in the kernel.
So maybe at one point device couldn't be into generic power domains. I know there was some work to kind of fix it. Do you know if that's been fixed?
There is support now available for, yes, there is support for a device to have multiple power domains. I think Wolf is having a hacking session tomorrow on that if you're interested in attending. Yes. What's that? Oh, okay. I don't know. Yeah, we'll figure it out. But yeah, but there is, it's on Pathable, and there is a hacking session on generic power domains. So, in case anyone is interested. Okay, so in the kernel, there has to be a little bit of platform-specific code that deals with the platform-specific part of powering down the power domains, for which the power off and power on needs, okay, I don't know why it is, okay, I don't know why it is like this, but anyway. So there is the power off hook and the power on hook, which have to be specified by the platform-specific code. And also an init of the power domains have to be done using PM gen PD init. Okay, I'll come back to set performance state in the next slide. So the slide, it's based on Runtime PM. So yes, so the powering down of the power domain is taken care of internally by the framework. When the idea is that if all devices in the system request to be active and idle through Runtime PM kind of knows whether the devices are active or idle. So Runtime PM can keep track of that and make sure that devices that are grouped together, if the devices that are grouped together are idle, can in turn go ahead and idle the power domain as well. And similarly, if a device in a group is requesting to be active, again Runtime PM can keep track of it and go ahead and activate the power domain as well. So when all devices in the domain are suspended, GenPD power off is called, which is the platform specific, that's the platform specific hook. So the hook is called to actually power down the domain, and then similarly when the first device in the domain is resumed, power on is called for the corresponding power domain. So very recently there is a dev PM GenPD set performance state added, which is more like the idea is that power domains can also have multiple performance states associated with it. It can be power levels or even clock levels or however you want to call it. It can be just SOC specific, but devices in that power domain can request for the power domain to be active at a particular level than just saying, okay, power on the domain, say be on at a particular level. And this is the API to do that, and which in turn will call into the set performance state, the platform specific set performance state specified by the driver, which is why we have it there. Other than that,
is the parameter to set performance state just like an integer, like a level, or?
I think it's a state. It's a int state, if I am correct. Yes, yes, okay. It's a state. So, and there is governor associated with GenPD, but it's not the conventional governor associated, like the governors associated with CPUFreck or CPU idle, where a particular state is chosen. It is more like, okay, if there can be quality of service constraints put on a per device basis, and the governor is basically to take care of, to make sure that those decisions are adhered to. And the power, like if someone says that, okay, fine, the power domain should not, I need a particular latency from a power domain, maybe the governor will take the decision not to gate the power domain even if all the devices in the power domain are idle. Okay. And then there is this PM quality of service framework. There are two classes of constraints, if you want to put it in that way. There are system-wide constraints that can be placed, and there are device-specific constraints that can be placed. So under system-wide, the main one is the CPU DMA latency, where any subsystem in the system can request for a particular latency, which in turn will mean that, which in turn translates to the C state the CPUs are put into. So this is one of the parameters that the CPU idle governor considers when choosing a particular C state. There are a bunch of other system-wide constraints as well, like network latency, network throughput, memory bandwidth, and then there is device-specific latency that I was talking about earlier, pertaining to per device. So because now there is device-specific latencies that can be specified, and CPUs are treated like a device, there can be per CPU constraint, which means one need not go through the system-wide constraint to put a latency constraint. So if you know that only one CPU needs to have a latency constraint or a shallow C state, the particular CPU can be chosen, can be targeted and for a shallower C state, rather than forcing all the CPUs to be in a shallow C state. So that is, I think, pretty much it. Yeah, so this is the original presentation from where this presentation has been adapted from. And I think that's it.
So Tara, in the previous slide, why is it called DMA, CPU DMA latency? Like it has something to do with DM. So that's basically the same thing you were talking about with the idle
CPU idle
residency
yes,
stuff, right?
Yes, yes.
So if it's
I don't know why.
Okay.
It has been there forever. I think it is just legacy.
Yeah.
Yeah. I don't think there's a particular reason for it. It has just been there forever, I guess. Yeah.
Okay.
Yeah.
So the idle governor will read that value and
Yes, the menu governor will
Okay.
take into account the value set for this.
Okay.
Yeah.
Cool.
Okay, so I think that's it. Thank you very much.